It's a preliminary work that I'm talking about air injection rate effects in light oil recovery. So, as previous speaker have already said that basically oil recovery increases basically amount of the crude oil in the field, and there are many ways to do it. But we are focused on the air injection, which leads to in situ combustion in the reservoir. Well, it's basically inject air, and the combustion happens, and then the energy is transported, and the oil is also collected in the other area. There are many effects that happens in the domain, like reaction, vaporization, condensation, and basically, our goal is to identify what's happening inside the domain if we have changed the oil injection rate. The air injection rates, and compare the pressure and permeability effect in different type of regimes. Well, model. For modeling this kind of phenomena, we have basically two phases. One phase is the air, which has oxygen, and the other we have the domain of oil in the domain, light oil in the domain. Our model does not consider the reaction in the gas, and the oxidation happens in the liquid phase, actually, which the hydrocarbon that has one single component to represent all components in the oil combusts with oxygen and can produce some gas. We neglect the water in the domain, and we consider only one-dimensional flow in the positive direction x. Well, we neglect the gas in the liquid diffusion, and we consider ideal gas as well. Well, these are the equations. This is basically the continual works of Nega that we also consider the similar model that she has, that one of the first equation, equation 2, actually, we have the liquid saturation equation, which has a temporal derivative and space derivative, the reaction and the vaporization. The second equation is the gas phase, which has the same component, the same terms, also the reaction and vaporization. And one is the hydrocarbon equation, which also has the vaporization but no reaction in the gas phase. And the oxygen in the gas phase has only the reaction terms. Well, for closest equation, we have like thermal equation, the energy equation, that we consider the rock and the liquid, and everything has the same temperature. And for the liquid phase, we don't consider capillary effects, liquid, and total derivative loss is represented like this. Use two different permeability for two phase. And the equation 8 and 9 has the permeabilities, which has the residual liquid saturation to control the permeability in the domain. Well, the model that we consider for vaporization has the equilibrium, which we have a evaporation rate constant, and the equilibrium consider Claus-Kepler relationship for calculating the equilibrium in the phase. And it has a porosity and a density of gas and saturation. Well, as we only consider one reaction, we have this term reaction that has liquid saturation, pressure as a compressible flow, and the gas, obviously, and the press potential terms and energy activation for that. Well, as we did the simulation, as we are implement in-code house for that, for modeling this kind of flow, we set up some test case that has this boundary conditions. We have an initial condition that specify a ramp in the liquid saturation and equilibrium initially, and there is no oxygen in the domain initially. In the left boundary condition in the domain, we have temperature that's initial as the air injection and the oxygen injection, like represented too, and the gradient of pressures is also in the upstream of the domain. And downstream, you have the gradients are 0 and a specified pressure reference for our simulations. Well, in the discretization, we use basically, for solving our system of equation, we use basically finite difference method. We use central difference schemes, second order, like in this sense, and backward implicit order method, and with adaptive time step in order to control the convergence. This discretization leads to a nonlinear equation that is solved with a Newton, incomplete Newton, that used to avoid the divergence or relaxation parameters that control some peaks of the oscillation of the solution. As a technique to solve the system of equation, each time step of our method for the coupled equation that are hydrocarbon and oxygen and liquid saturation and gas saturation are solved coupled. And each equation has can be used with one times different time step. And then after solving this 4 equation coupled, there we use implicit and split method to solve Darcy velocity and pressure. And for a pressure equation 2 and 5 are combined to produce a pressure equation, and it's solved separately, and then the velocity is calculated. Basically, we have 4 equations coupled, and pressure and velocity equation are calculated explicitly. Well, for a test case of our code, we use those parameters that was taken out from Alexei paper, 2013. We use a match of 2,000 points, which is fine enough to capture the multi-scale, and a time step was calculated based on CFL for velocity and pressure equation, and then we use subcycling to calculate the time step for the coupled variables. Like it was calculated this time step experimentally. We test which time step would be used compared to CFL. Like for pressure equation, we use, for instance, 0.1 delta T, and for saturation course, we use 0.01 delta T. So this is our test case base, and we changed injection velocity, pressure reference, and permeability. Well, this already results. In this first case, the case where we have air injection rate of 0.1 meters per day, taken by Neger. And as you can see, the oxygen is totally consumed in the beginning of the domain, in a thin region, and the temperature got like most reduced fastly, and you have the hydrocarbon here, which has a peak here in the small region. On the other hand, when you have air injection rates of 100 meters per day, the oxygen is not totally consumed. And the profile of temperature changes once the temperature is proportional to the velocity. So you have a higher temperature, and you have also a non-oxygen that's not consumed. However, the profile of oil saturated is still almost the same. Well, we can see that there exists oxygen breakthrough in this case if you increase the injection velocity. In another case which I change the permeability in order to reduce the oxygen breakthrough, also with 100 meters per day of air injection rate, the oxygen breakthrough still exists. However, you can see that the temperature was reduced once the pressures, in this case, will be higher. So another case, I decided to increase the pressure, reference pressure, and you can see that the temperature was reduced and the hydrocarbon was also reduced. Once we increase the pressure, the boiling point of the hydrocarbon also increased. However, and also you can see that the oxygen breakthrough still exist. And in this case, the consumption of oxygen is less, actually, of the other case. Here is the same case to compare the result, that we can see that the total different behavior of the oxygen consumption. Well, here's the transient simulation of the two cases. One case is 0.1 meters per day, and you can see that the oxygen is not consumption, is consumption and goes through the domain. And the other case that we have higher velocity injection, the oxygen is not totally consumed, and the wave still cross the domain. Oops. Oh yeah, it's here. Now it's not changing the slide. It's not changing the slide. No way. Let me see. Okay, this the reference is like it's a work in development that has been done in like 3 months actually, and some reference. And we have this prevalent conclusion that when the air injection rate is high, the oxygen propagates along the distance inside the container oil region, and this is undesirable due to the danger of oxygen breakthrough at the production well. The increase of pressure also reduces the oxygen consumption, and the danger of breakthrough is still even worse. Increased permeability does not affect significantly the combustion wave structure. So that's what I have to say. Thank you.
We have a lot of time for questions.
Yeah, I told you that. It's the previous